Hey guys, in this video I'm going to talk about Pascal's triangle and how it relates to the binomial coefficient. Um, so I'll start by expanding some binomials. So over here we have a plus b to the power of 1 equals a plus b squared equals a squared plus 2ab plus b squared. And notice in our Pascal's triangle we have 1, 2, 1, and the coefficients are 1, 2, 1. Similarly, a plus b cubed, we have a cubed plus 3a squared b plus 3ab squared plus b cubed. The coefficients in the Pascal's triangle are 1, 3, 3, 1. And over here we have 1, 3, 3, 1. And we can also do a plus b to the 0. It's kind of its own thing, but you get the idea. And in general, we can say that this number here is number n, so these are all a plus b to the n. So this is row 0, row 1, row 2, and row 3. So it definitely looks like there's some kind of pattern going on with the coefficients of the expansion and Pascal's triangle. But what I'm going to do in this video is basically show you why these two facts are the same. Make it obvious why Pascal's triangle has got anything to do with binomial expansions, and show you why it's not just some kind of coincidence. So what I'll do is I'll start with the expansion of a plus b cubed and show you why Pascal's triangle will be able to predict what the expansion of a plus b to the 4 is. So if we have a cubed multiplied by a plus b cubed times a plus b is a plus b to the power of 4. Now, even though I don't yet know what the coefficients will be, I still have a general idea of what the binomial will look like. So I have something times a to the 4 plus something times a cubed b plus something times a squared b squared plus something times a b cubed plus something times b to the 4. And I know that these are the, and even though I don't know what the coefficients are, which are represented by these blank lines, I do know that these are the only combinations of a and b I can get. So why is that? Well, the first reason is obviously we can't have 5 or anything, because the best we can do is a cubed times a will just give us a4. But we also can't have things like, say, a cubed b squared, because to get something like that we need an a cubed b times b, or an a squared b squared times a. And as you can see, that's just we don't have that. We don't have the a cubed b, we don't have the a squared b squared. So what all of these have in common is that they're just one of these, but you add a power to them. So let's work out the coefficients. To get a to the 4, the only way we can get a to the 4 is a to the 3 times a. So we do this times a, and that gives us a to the 4. The coefficient of this is 1, the coefficient of that is 1. So if we look at our Pascal's triangle, that's why the 1's just sit on the ends there. Now let's look at our a cubed b. There are actually two ways to get an a cubed b out of this. We can get this 3a squared b and multiply it by a. So that will give us 3a cubed b's, but we can also get this a cubed and multiply him by b. So that will also give us an extra a cubed b. So 3 plus 1 is 4. And over on Pascal's triangle, 3 plus 1 is 4. And with our a squared b squared, we have our 3a squared b. We can multiply by b, and our 3ab squared multiplied by a. And 3 plus 3 is 6. As you can see, 3 plus 3 is 6. And the pattern just continues. I'll show you anyway. We have the 3a squared b times b and the b cubed times a. 3 plus 1 is 4. 3 plus 1 is 4. And yep, b cubed times 1 is b to the 4. B cubed times b is b to the 4. And of course, I didn't have to do this game with only the cubed. I could have done it with any of the terms. So that's why Pascal's triangle does this. And to reinforce that idea, I'll show it again. And this time we'll be obtaining this one. So I'll write this out. And to get a plus b to the 5, we'll multiply by a plus b. And once again, I know the coefficients will have to look something like this. Whoops. Now, once again, we have a to the 4 times a, which is why the 1 goes to a 1. We then have to get our a to the 4b, we have this guy times a, and this guy times b. So 4 plus 1 is 5. 4 plus 1 is 5 over there. To get the a cubed b squared, we have a cubed b times b and a squared b squared times a. 4 plus 6 is 10, and 4 plus 6 is 10. And to get our a squared b cubed, we can do this by b and that by a. Once again, 4 plus 6 is 10. 4 plus 6 is 10. And the pattern continues like that. So this is why the Pascal's triangle is related to our binomial coefficient. Now, there's another cool fact about Pascal's triangle. I'll have to draw a new one over here. So let's look what happens when we add up the rows of Pascal's triangle. So the top row, I remember this corresponds to n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. So the top row, pretty simple, is just 1. The second row, 1 plus 1, which is 2. Then the third row, which is, okay, the n equals 2 row, I ought to say, 1 plus 2 plus 1 is 4. 1 plus 3, that's 4. Plus 3 is 7, plus 1 is 8. And if you can just add those up, you'll see that we get 16 and 32. And there's a pattern here. These are all powers of 2. 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the 4, 2 to the 5. And like before, I'll show you why this is true and why it's not just a coincidence. So, as we I'll give you an example with, say, this one. A plus b to the 4 is equal to a4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4. Now what we can do is we can replace our a and our b with 1s. So I'll have 1 plus 1 to the power of 4, which will be 2 to the 4, which is 16. But we can also use this thing. Now, since a and b both equal 1, that's just going to equal 1. This thing is going to equal 1. This thing is going to equal 1, and so on. So we'll simply be left with 1 plus 4 plus 6 plus 4 plus 1. So that's why this row gives us 2 to the 4. And I'll do it again. So a plus b to the power of 5 is equal to a to the 5 plus 5a to the 4b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the 4 plus b to the 5. And once again, if we let a and b equal 1, we'll have 1 plus 1, 5 is equal to 2 to the 5, which is equal to 32, equal to 1 plus 5. Remember these, it's just 1 times 1, it's just 1, plus 10 plus 10 plus 5 plus 1. And of course, I didn't have to do this with n equals 4 or n equals 5. I could have done this with any number. I could have done this for any value of n. And it would have still worked. I would have still been able to do this very same process. So that's why the rows of Pascal's triangle add up to powers of 2.